Hi, welcome to the Unit 3.1 Thermodynamics video. In this video, we're going to focus on the second key question. How do we quantify energy transferred during a chemical or physical change? This video is part 1 of 2. So before we get started, I kind of want to ground you in why this is important. Chemists, whenever we're doing a chemical reaction or looking at a chemical reaction, there are two main things we want to focus on. How fast the reaction goes and how far it goes, along with how much energy is lost or gained. So how fast is kinetics, and we're not focusing on that right now, but that's also something that's super important for controlling and understanding a reaction. Thermodynamics focuses on how far a reaction proceeds. Does it go all the way or only partial the way? Is it in equilibrium? And how much energy is lost or gained. Before we move on, I want to talk about what energy is, since we're focusing on thermodynamics and we want to know how much energy is lost or gained in reaction. It's the capacity to do work. And so this is a physical term, and this is one of the reasons why physics is the fundamental or the founding science, because we're using the same sort of principles you use in physics. The units for energy are joules, so you need to get used to seeing that. There are other units such as calories, and of course you can put the prefix kilo in front of joules, kilojoules or kilocalories. But we're here we're going to be utilizing joules. The more energy you have, the more work you can do. So if it's the capacity to do work, if you have a lot of energy, you can do a lot of work. And once you do work, you're going to lose some of that energy. So those are the sort of things that you need to keep in the back of your mind. Now, why is this important? One of the reasons why this is important is that we utilize chemical reactions to gain energy or to do work. And an example of that will be the combustion engine. So this was an old school combustion engine, one of the first combustion engines. And then you have a more modern sports car. So by understanding chemical reactions and the energy that we can gain from combustion, we've been able to design better engines to utilize that energy. Another reason why this is important is in designing better drugs. So one thing when designing drugs is sort of to focus on interactions, and when things interact, you can lose or gain energy because of that interaction. So that process can be understood more through thermodynamics. All right, now you know why that is important, and you know that energy is the ability to do work. What are we going to be doing exactly in this video? We're going to look at first the law of conservation of energy, and the next thing we'll look at is how energy is lost or gained during a chemical reaction. And finally, we're going to look at a heat of a chemical reaction. These are the equations here at the bottom that we're going to be focusing on. All right, so let's start off with some laws. Laws sort of ground us in the ideas and the content that we're looking at. There are 4 laws of thermodynamics. We're not going to focus on all 4 today. We're really just going to look at the first 2, the 0th and the first law. And we're actually going to start with the first law, law of conservation of energy. This may sound familiar to you because you've heard of the law of conservation of mass. Actually, the law of conservation of energy and mass are equivalent. But anyway, what it means is that energy cannot be created nor destroyed. So the change in energy must always be 0. To fully understand that, we have to sort of take a moment to think about something called the system and the surroundings. So the system is the part that you care about whenever there's a process and you're focusing on this one part. That would be the system. The surroundings would be everything else, and the system and surroundings can exchange energy. So that's important to know. So since they can exchange energy, but the overall energy must be 0, that means that the delta E of the change in the energy of the system and change in its surroundings, again, must be 0. So that means that these two must be equivalent. The only way that delta E overall can be 0 is if the change in the energy of the system is equal to the change in energy of the surroundings. So if the system loses energy, the surroundings will gain the same amount. Okay, so now let's talk about the system itself. Let's focus on that part. Energy transferred to and from can be transferred to and from the system by work or heat. So the surroundings can give energy to the system or the surroundings can gain energy from the system. In other words, the system can gain energy from the surroundings or lose energy to the surroundings. And there's two ways that it can happen. It can happen through work and heat. So delta E of system is equal to heat plus work. And since this is thermodynamics, we're really going to focus on the heat part. And so let's take a look at that with heat. There are two processes here. One where the system can lose heat to the surroundings. And when the system loses heat to the surroundings, that's called an exothermic. So you think of exit, heat is being lost. And you can see that in this diagram here. So what happens when the system loses heat to the surroundings? The surroundings, because you can use the thermometer to measure the temperature of the surroundings. The surroundings, the temperature will go up. It will increase because it's gaining this heat energy. So, in case of exothermic reaction, they're going to feel warm. So an example of that would be a combustion reaction is exothermic. It's losing heat to the surroundings and it's going to feel warm. The system itself, however, it's losing heat, so its energy is going to go down. Endothermic, on the other hand, is when the heat energy is gained by the system. So here you can see in the diagram, the arrows are pointing in towards the system. The system is gaining this energy. And so what happens to the surroundings is, since it's losing the energy, the thermometer will read lower, although the system itself is gaining energy. All right, let's try the CFU. So what I want you to keep in mind is how heat energy is transferred. So it says a cup of hot coffee feels warm in your hand. So you got to explain, why does it feel warm in your hand? And I want you to consider terms exothermic, endothermic, or lose or gain heat. Pause the video now and try your best to sort of explain, why do you think it feels warm in your hand? Great, so you should say something that the coffee is transferring or losing heat to the cup and your hands. And so that's why it feels it's going to feel warm, because your hand is actually gaining heat from the coffee. And if the coffee is a system, then the system itself is actually going to be losing heat energy. So your hand is gaining heat and the coffee is losing it. And we would say this process is exothermic if the coffee is the system. All right. Now that we talked about heat being transferred between system and surroundings, something to note is that not all heat transfer are equal. There are several factors that control how much heat can be transferred, and that means lost or gained, by a system. So we're going to look at that in a moment. But first, I want you to think about this would you rather question. Would you rather have 1 gram of boiling water poured into your hand, or 100 grams of boiling water? Okay, most of us would probably say 1 gram, and that's because we would know the amount of heat transfer depends on the amount of water. So if you had 100 grams, you're going to of boiling water poured into your hand, 100 times more energy will be transferred to your hand than with 1 gram of water. So that means you're going to get a major burn for 100 grams of water. But 1 gram of water, you get a burn, but it won't be that major. So one factor that controls heat or energy transfer is the amount of the substance. The next question I want to think about the factor is what would take longer to heat, 10 grams of iron or 10 grams of water? So we have like a match here, and just imagine you took a match and you try to heat iron and water with that match. What would take longer? Okay, so you would probably know that it would take more energy to heat up the water than the iron. And that has to do with something called heat capacity. Water has a higher heat capacity, and that's why it would take more energy. Metals usually heat up pretty quickly, but it takes a little while to heat up some water. So let's talk about what heat capacity is. Heat capacity is the amount of energy it takes to raise a substance 1 degree Celsius. And it can be given as heat capacity, in which case the units are joules over degrees Celsius. And for that, the equation for heat will be Q is equal to C times delta T. Delta T is the change in temperature. Or it could be specific heat capacity, which is given in joules per grams degree Celsius. And that's called specific heat capacity because this one depends, shows the dependency on mass, where Q is equal to MC delta T or Q is equal to MS delta T. So sometimes you'll see specific heat capacity written as S or a lowercase c, and heat capacity is usually written as a capital C. Okay, so we're going to focus on the MCAT one, where Q is equal to MC delta T. And so these are the components of the heat equation. So Q stands for heat, and we can measure it using this equation. Okay, the next thing we're going to talk about is thermal equilibrium. That's known as the zeroth law, and we're going to use that to sort of help us see how we can utilize this equation. So thermal equilibrium states that if an object at different temperatures are in contact, they will become the same temperature. So let's take, for example, we have a mass, 58 grams of iron, and it's heated up to 400 degrees Celsius. And we're going to drop this hot ball of iron into 300 grams of water, and the water right now is at 10 degrees Celsius. What's going to happen to the temperature after they come in contact and they sort of get a chance to settle? Right, the temperature should become the same. So the temperature of the iron and the temperature of the water should be the same. Now the question is, and that's what thermal equilibrium is about. Now the question becomes, what's the temperature going to be? Is it going to be an average of these two or somewhere in between these two? Is it going to be higher than the temperature of the iron, lower than the temperature of the water? What do you think the temperature is going to be? Actually, for this system, the temperature is going to be 18 degrees Celsius. And let's take a look to see how did that happen? Because 18 degrees Celsius is much closer to that of the water than of the iron. Like, it's not really in between, because in between would be like somewhere in the 200s. So what's going on here? So in order to understand that, we're going to utilize this equation, MC delta T. And what's happening here is that the heat, remember, going back to our laws of thermodynamics, heat lost by the iron will be gained by the water. So we can write that as Q of Fe equals Q water, and we're putting the negative here because the iron is losing heat. So the sign for heat loss is going to be opposite than heat gain. And to get the signs to be the same, I'm just putting a negative in front. Now, if I go ahead and plug in everything into my MC delta T equation, the mass of the iron is 58 degrees. The specific heat capacity is 0.450 joules per degree Celsius and grams. And then the delta T is going to be the T final minus T initial. Now, the T final for the water and the iron are both 18 degrees Celsius because they reach thermal equilibrium. And the initial temperature was 400. I do the same thing with the water. So I subtracted those two values to get the delta T of Fe. And then I do the same things for the water. I plug in my mass. This is the specific heat capacity of water. You'll see this a lot. And then I plug in my final temperature and initial temperature. What I want you to do is I want you to prove that these two are equivalent by doing the math. You want to use just 2 sig figs here, since that's really what we're limited by. We're technically limited by 1, but you can do 2 sig figs here. So why don't you pause the video now and check to see if you, with 2 sig figs, if these values are going to be the same. Okay, yes, they are the same. So you should have 1.0 times 10 to the 4th power, and you'll notice that for the iron there's a negative in front here. So we just, again, that's why we have that -1 on the outside to make these to be the same. So both sides are now equivalent. So one thing that you may notice is that the delta T for the iron is going to be much greater than the delta T for the water, and that's because because iron has a smaller heat capacity. So the heat capacity value here is only 0.45, whereas for water is 4.186. So a smaller heat capacity means it's going to gain, its temperature is going to change a lot more rapidly with just a small increase of heat. All right, now you're going to try this CFU. With that understanding about how heat capacity will determine the change in the temperature, read through these experiments 1 and 2, and then based on the 2 experiments above, which metal, copper or iron, has a higher specific heat capacity? Be sure to explain. All right, so the answer is iron has a higher heat capacity because it has a smaller delta T. So the larger the delta T, the smaller the heat capacity. The smaller the delta T, the higher the heat capacity. Okay, the last thing you're going to do here is there's a video linked in where you're going to watch on how to use this equation more. There's a bunch of example problems. You're going to try to solve each problem on your own using your algebra skills. And take notes. Be sure to take notes in the space that's provided in this packet. Have a quality day.